Introducing derivatives, part 1. Suppose a stone is launched vertically upward with an initial velocity of 96 feet per second from the river. By Newton's laws of motion, the position of the stone measured as the height above the river after t seconds is s of t equals negative 16 t squared plus 96 t. And that would be in feet. Let t represent a particular time, and let t plus h represent a very short time later. What is the average velocity of the stone for the time interval t to t plus h? So if s is position, the average velocity on the time interval would be the change in position over change of time. Looking at the denominator, t plus h minus t is just h. Next, how do you evaluate your position function at the time t plus h? And then how do you evaluate it at t? And what is the difference? So this is the algebra that we need to do. It's going to be a little bit messy, so we will continue our work on the next slide. So average velocity. Average velocity, let's see. Let's square t plus h, and let's distribute the 96 and let's distribute the negative. When we do that, we get the second line. Continuing on, let's combine 96t with negative 96t, and let's distribute the negative 16. After we do that, we can cancel the 16t squared with the negative 16t squared, and then divide by h. In summary, the average velocity from the time period of t to t plus h, over that interval, the average velocity is negative 32t minus 16h plus 96, and that is feet per second. To find instantaneous velocity, we would make the time interval shorter and shorter, which is equivalent to saying that we have h get smaller and smaller. So if s is our position, then instantaneous velocity will be our average velocity with h getting smaller and smaller. And for this particular position function, our average velocity is negative 32t minus 16h plus 96. As h gets smaller and smaller, this becomes negative 32, that should be 32, negative 32t plus 96 feet per second. So starting with a position function, we found the instantaneous velocity through this limit process. In order to generalize this to other fields and circumstances, we need only make a few minor adjustments. The function that gives the instantaneous rate of change of y equals f of x is called the derivative function, f prime of x, and it is found by evaluating the limit of the average. In addition to the notation f prime of x, you will see a wide variety of notations, and I've given three notations. You'll see dy dx, y prime, and d sub x of y. For our position function, s of t equals negative 16t squared plus 96t, we found the velocity function by the limit process. So we now know that this velocity can also be written as the derivative of the position function s prime of t, or even ds dt. We will continue this discussion in part 2. Take care, and I'll see you then.